Hello guys, my name is Lazaro and today we're going to be doing a LeetCode problem. This problem is called Construct the Lexicographically Largest Valid Sequence. Given an integer n, find a sequence that satisfies all of the following. The integer 1 occurs once in the sequence. Each integer between 2 and n occurs twice in the sequence. And for every integer I between 2 and n, the distance between the two occurrences of I is exactly I. So this last one, I believe it's the most confusing one out of all of them, but it's basically saying every number between 2 and n. Let's take, for example, 2. Since we're going to be returning an array of integers, the distance between the first two and the second two has to be 2. The distance between the first 3 and the second 3 has to be 3. And then so on and so forth up to n. So that means, if we look back at this constraint right here, 1 is only going to occur once, so we don't really have to worry about of having two ones right next to each other. So from just these three rules that we have to follow, we get a pretty rough idea of what we're supposed to output. The distance between two numbers on the sequence, a of I and a of j, is the absolute difference of their indices. So this is basically saying that it goes both ways. The distance between the first two and the second two is just the difference of their indices, and the distance between the second two and the first two is with the exact same thing but absolute value. So we don't have to deal with the negative distances. Return the lexicographically largest sequence. It is guaranteed that under the given constraints, there's always a solution. So this right here is pretty good. We don't have to worry about returning an empty array or -1 or whatever if the constraints were not able to be satisfied for the given n. So now the confusing part of the question we might have is, well, what does lexicographically largest sequence mean? If there's two sequences, how do we know one is larger than the other? Well, they actually tell us. A sequence A is larger than a sequence B of the same length if in the first position A and B differ. If in the first position where A and B differ, sequence A has a number greater than the corresponding number in B. So they also give us an example right here. They have sequence A is 0, 1, 9, 0. And then sequence B is 0, 1, 5, 6. Now they only differ in this third position right here. The first 0 and then the 1 are similar in both sequences, but the difference is the 5 in B and the 9 in A. Now since 9 is greater than the 5, then we say the sequence A is the greater sequence, or the lexicographically larger sequence. Now let's get into the examples. Right here, the first example, we have n is equal to 3. So we already have a couple of ideas how this output array is going to look like. We know we're going to have two 3s, two 1s, and then just one 1. That also tells us we're going to be dealing with numbers between 1 and n. Our array is going to consist of numbers between 1 and n. Now, we have multiple sequences here that we could build with this constraint. For example, we can build out 2, 3, 2, 1, 3, and also 3, 1, 2, 3, 2. But this sequence right here is larger than the first one I mentioned, because at the first location where they differ, where in this case is index 0, this sequence has a number that's greater at that index. Therefore, this one's lexicographically larger. Now, one idea you guys might be having is, well, if we want the largest possible in every index, because that's basically what it's asking us, at every index, try to put the largest number possible here, so we know for sure that we're building the lexicographically largest sequence. With that, we know we have to build out a greedy solution to this. So let's get right to the drawing and see if we can figure something out. With n equal to 3, we have the correct answer of 3. I actually didn't read it all. It was 3, 1, 2, 1, 2, 3, 2. Notice how this satisfies the constraints. There's only one 1. There's two 2's, and the distance between them is 2. This is 1, and then this is 2. There's also three 3's. The distance between them is 3, 1, 2, and 3. So this is the correct output array, or the output array we really want to be accepted, that we want to output for this n right here. Now, we've already talked about greedy. We know that greedy is the right approach because at every index we do want the largest possible at that position. That obviously makes sense because from there we'll be guaranteeing ourselves the largest lexicographically sequence, the largest lexicographic sequence. It's a large word. Anyways, so let's say we start off with an empty array. Let's say we only have 3. We do not know what our output is supposed to be. From this, can we figure out how many numbers or how many elements are going to be inside this array? AKA, do we know the size of our array from just n? Well, if we remember back to our constraints, we know that every number will occur twice except one, who will occur once. So if we know that every number is going to occur twice except one, then we can basically say that n times 2 minus 1 will give us the size of the array. Because let's say we have n times 3, that'll be 6. So we have 6 positions. So this could be 1, 1, 2, 2, and then 3, and then 3. So 2 spots for every single number. So that's why we're multiplied by 2. But the 1 is only occurs once. Therefore, we need to subtract 1 to get the correct answer. And as you can see, this is exactly the size of this array. There's 5 elements in here. 3 times 2 is 6. 6 minus 1 will be 5. Perfect. So now we know how to calculate this size of the output array. So let's just call that right here. Size is going to be equal to 2n minus 1. So let's create this empty array. Right here we have 5 elements. Now at the first position, let's try 3. Let's see if we can place 3 in this position. If we were to place 3 here, then we also have to place 3 at a distance of 3. So let's write down the indices. There we go. Now 3 plus the current index will give us just 3. And that just happens to be, that was weird, 3. And that happens to be the correct location where we want to place it. So at this index, if this index is available, if we can place a number here, then place the 3 here. And also check if at a distance of 3, if that location is available, also place 3 there. So, okay, we've tried 3 in this location. Now, let's say we're doing this in a recursive function, which, just a little hint, we will, because we will want to backtrack. The reason we want to backtrack is because let's say at a certain location, let's say here I have 2, right? I cannot place 2 here. And let's say I have another number, uh, let's just say, let's cut it at 2. Let's say I have no other numbers that I can place in this location. I will want to backtrack to 0, and now I would want to try, instead of 3, maybe try another number here. In this case, I am going to be sticking with the 3. So now we moved from index 0, and now we're index 1. At index 1, would we want to try 3 again? Well, the answer is obviously no, we wouldn't, because we've already tried 3. So we need to keep track of the numbers we've tried, and we also need to be iterating backwards from n. So let's take it back one more. Let's start from 0 again, so we can build up this logic of ours. So at this location, at index 0, we can possibly use all the numbers, everything from 1 to n. And we want to iterate for this position right here. We want to first look at the largest possible. So let's first try n. If n doesn't work, try n minus 1, and then so on and so forth until we reach at 1. So here we're first going to try 3. This index was available, so we could place 3 there. And the index at a distance of 3 is also available. So let's try a 3 there as well. Now, once we move to index 1, our range has decreased. The numbers we can use is 1 and 2 only, as opposed to the beginning, where we can use 1, 2, and 3. Here we can only use 1 and 2. So since we're trying the largest possible first, let's try 2. This index is available, so let's place a 2 here. At a distance of 2, we have a number there. So we know that we cannot place this 2. Instead of placing a 2, we must try another number. Well, since we're moving backwards and 2 didn't work, our only one remaining is just 1. This index is available, so let's place a 1 there. Now this is a special case. Since the number we're looking at is 1, we don't have to worry about placing the same number at a distance equivalent to it. So we place the 1 and then we carry on. Now we're at index 2. At index 2, the only number we can use is 2. Well, therefore this location is available. Let's place a 2 here. And the index that is a distance of 2 is also available, so let's place the 2. Next we get to index 3. We have no numbers, we have a null set. That might look to 0, like a 0. I think the null set is like that. It's either like that or it's slashed, I'm not sure. But we have no numbers available to us at this index, and this index is already occupied in our array. So let's continue. Let's go from 3 to 4. Whoops. Looks like I was erasing and forgot to drop back that part. There we go. So now we're at index 4. We have no numbers left, and this index is already occupied. So let's carry on. And now we're outside of the bounds of this array, so we know we can finish. We can successfully stop searching for a sequence. Now, using this greedy approach with backtracking, like a perfect example of the backtracking part was how we were trying to put a 2 here, but we couldn't because there was already 3 at a distance 2. So we need to use this greedy approach with a combination of backtracking to successfully find an algorithm that solves this problem. That's really the main thing we need to solve this problem. We just have to keep in mind where we're currently on. For the index we're currently on, is it available? Furthermore, do we have numbers that we can use for this index? And then finally, at a distance at the number we're considering, is that index available? So now let's try to take what we talked about and what we discussed and actually put it into some code. First, let's build out that size of the array, which is going to be equal to 2 times n minus 1. Then let's actually build out the array itself. And I'm going to initialize it all to -1 for now. This way, I know since all the numbers are going to fall between the range of 1 and n, if I can use some number, could have used false, I could have used none, I could have used 0, I'm using -1. As long as I have a number here that tells me that this index has not been taken just yet, that's all I need, and that'll be more than fine. Next, let's build out our recursive backtracking function. We're going to want to take in as a parameter the current index we're looking at and the numbers available to us. This numbers available to us is going to be a set, and that's how we will know if we can use this number or not. In this case, I'm kind of doing the opposite, where seen is really the numbers that we could not use, or you can do it the way we discussed about, where seen or whatever other variable name you probably call it, can use or available, it will contain the numbers you could use. But I'm going to do it pretty much the inverse of that, where it tells me the numbers I could not use. So for now, we want to check if the length of seen is equal to n, or I is greater than or equal to the length of the array, aka the size we calculated, then we want to return true. The reason we're returning true is because this if statement is checking if we have already used other numbers or if we're out of bounds. Another if that we're going to want is if self.array or self.r at this index does not equal -1, then we know we're in a position that is currently occupied by a number already, and we don't want to override this index. Therefore, let's just return whatever the next index gives us. Now with this base case out of the way, we want to start our for loop. So for every index in the range of n, and we stop at 0, and we're going backwards. Now this is how we do it in Python. I believe in other languages you have to do int I is equal to n, while n is greater than 0, n minus minus. I think that's how it would be for C++ or Java. But just understand, this is how we're going iterating backwards, starting at n and then finishing at 1 in Python. And it's exactly what we talked about in the doodle, or in what we were drawing. So IDX is really going to represent the number we could use. So I'm just going to call it num, actually. It's going to represent the number that we're considering. If this number is in our seen set, aka if we've used this number already, let's not even consider it, and let's just continue and go to the next iteration. In addition, if the current position we're on plus this number is greater than or equal to the length of our array, also known as the size of our array, and the number is not a 1, we want to also continue. This is checking, whoops, this is checking where, let's say we're at this last, one of these last indices right here. Could we place a 2 here? For example, let's pretend this 3 never existed. Could we place a 2 there? The answer is no, but because to maintain one of our constraints, we have to put the second 2 at a distance of 2. And a distance of 2 will be out of bounds of the array. Therefore, this 2 should not be considered. So if that's the case, then we want to continue, and we're also checking if the number does not equal 1, because if it is a 1, then we don't have to worry about distance. Finally, the next if is checking if num does not equal 1 and the element at index I plus num, so aka the element at a distance of num array, if that one is occupied, then we know that we should not consider this number. So that's all of our ifs out of the way. And now we can actually get into the recursive or the backtracking and recursive function. We want to, since we're considering this number, let's add it to our scene set. Let's set this position in our array equal to num. And if the current number does not equal 1, then let's also set the index at a distance num away equal to this number. So with this right here, we're taking care of this constraint. Now we want to call this function recursively, increment our position, and also pass a scene. Now if this returns true, then we know we have found a sequence and we want to instantly stop. Else, if the number we're currently on does not equal 1, we want to set the element at an index of distance away back to -1. Because remember here, see how far back I can go. Perfect. Remember here, when we tried the 2, we're overwriting the 2 here as well. Well, in this case, it's going to check if there's not a number there in the first place. But if we were to come back all the way to the 3 and the 3 didn't work, we would try the 2, but before trying the 2, we must first erase this 3 at this index. So we try the 2, and when we put a 2 there again. But before putting a 2 there, we must erase the 3 that was formerly there. So that's what we're doing right there. And then after all of this, we want to remove this current number, because let's say if we go to the next iteration, we want to make sure to remove this number from our scene set, because once we call the function recursively, that's when we might use the number. And then finally, outside of this for loop, if none of this worked, then let's set it back to where it initially was, and let's put it as it's vacant and it could be used later on. And then return false if we never saw a true sequence, a sequence that worked in this for loop. Finally, all we would have to do is call this function starting at 0 with an empty set. and then return whatever self.array is. So let's run this, see if I made any mistakes. Okay, I didn't. Let's try more test cases just to make sure our solution is valid. Now let's submit. And perfect, it works. So hopefully this video was able to help you guys to solve this problem. As you can see, it's not the most confusing or challenging problem. It all has to depend on how you tackle it. The key part to solving this problem was realizing that this is a greedy solution or a greedy algorithm. So it's a greedy, once again, it's a greedy with a combination of backtracking and of course recursion. So a lot of fun topics, am I right, guys? All right, so other than that, hopefully you guys enjoyed. If you did, leave a like and consider subscribing. And thank you for watching.